Can you briefly describe what quantum computing is and what it can offer over classical computing?
So basically, a quantum computer tries to exploit the effects that you can find in the laws of quantum mechanics in order to do computations in a more efficient way in many cases than in classical computers. So there are many architectures that are being developed right now. So in my company, in Quantinuum, we have one of the leading ones, which is ion traps. And then there are
Hello, everyone. Welcome back to the It's a Material World podcast. I'm Puneeth, and here's David. So, David, anything new in your world before I get into a major update of mine? Not really major, but I just wanted to hear more about you since it's been a while since we've recorded.
Oh, well, now I'm super excited for your update. But no, not really. Just continuing to go and just work and then get all my actual adulting done. So got my insurance cards and everything, and so now I have to
Oh,
find doctors, unfortunately. But
oh yeah.
yeah, nothing nearly as exciting as this major news, which I'm very
Oh
excited for
gosh.
now.
Oh gosh. No, I know how busy it can get, and then it's hard to do like the adult things like finding a doctor and things like
Yeah.
that. So, anyways, that I think I overestimated how big the news is, but I think it's important for at least our YouTube viewers on our podcast. But I got a new computer. The previous one had some glitches that you guys may or may not be able to find on previous episodes. We tried our best to edit it out, but for some reason, Zoom it did not coincide well with my really old computer. So finally upgraded. I figured we hit triple digits with our podcast episodes. So it was time to make that upgrade. But that kind of goes hand in hand with the topic of today's conversation, where we get into quantum computers and specifically this intersection between quantum computing and how it can enable faster materials discovery. So I wanted to hear your thoughts. What was maybe your favorite part of the episode?
Yeah, I really liked how our guest David explained the use of quantum computing. And so it won't be used to replace classical computers, but we're going to be using a quantum system to describe a quantum system in materials design, selection, understanding, etc. And so I thought that was a really unique way of putting it that I'd never heard before. And it makes a lot of sense when you put it like that, is that we know that there's quantum like systems are very strong. He mentioned oxides for superconductors. And so I thought that was just like a very good analogy and a good way to think about it. And so I think that he was able to break down how it works to a high level and then also like the applications and what it could look like, which I enjoyed.
And I appreciated how real and transparent he was about the current state of quantum computing and what the future could hold, exactly as you mentioned. But he also talked about potential drawbacks, in terms of noise sensitivity and error rates, and potentially how to enable engineering innovations to overcome those obstacles. One other strong piece, he also gave very strong pieces of advice to material science and engineering students and young professionals in terms of what they should do or what they should focus on if they are interested in getting involved in quantum computing. I know when we were at Puzzle X back in November, Xena made it an emphasis to talk about quantum and just the rapid ascension of this industry and all the possibilities it could enable. So I do think there's a lot of potential for it, but right now it seems like it's in that stage where the applications aren't quite defined, but the potential is there and the kind of efficiency increases is there as well. So it seems to solve another set of challenges that classical computing doesn't. So
Yeah, I would just say that I think he also stressed the need for like the physical component, but also the software component, which I thought was interesting. And so it's going to be the combination of both. So there's a lot of room for development, both on like the modeling analytical side for material systems, which he said was like one of the highlight applications in his mind. And then also like the actual physical, how do we like encode and how do we like hold these qubits in space to reduce the most loss. So I thought that was very interesting as well.
yeah, and I could see how material scientists may have to have some level of skill set and expertise in both the hardware and software side to be able to create these models, but then also analyze them and then communicate and really dig through the findings and the results to be able to communicate that to, other functions, other parties, and really derive a lot of value from it. So without further ado, we'll get right into the episode, but I just wanted to mention, please, if you enjoy the episode or if you enjoy the podcast, leave a rating and review on your preferred podcast platform. It really helps us out a lot in terms of our growth, but really happy and really grateful for you all for listening and for joining us for this podcast journey. So let's get into it.
All right. Hello, everyone. For today's episode, we are lucky to have Dr. David Muñoz Ramo, the current head of quantum chemistry for Quantinuum, a quantum computing-based company. David earned his master's and PhD in computational chemistry from the University of Barcelona in 2004 and has since worked in computational science for 15 years. He was a research associate at the University College London, then at the University of Cambridge, before joining Quantinuum, where he has been for 5 years. Welcome to the podcast.
Thank you. Nice being here with you.
Yeah. So, David, there has recently been a lot of publicity and articles about quantum computing, but it may get muddied in the news that there are many types of quantum computers. So I know we discussed this at Puzzle X last year, but can you briefly describe what quantum computing is and what it can offer over classical computing?
Yeah, sure. Well, it's a bit daunting to try to summarize this technology in just a couple of sentences, but okay, let me try. So basically, a quantum computer tries to exploit the effects that you can find in the laws of quantum mechanics in order to do computations in a more efficient way in many cases than in classical computers. So there are many architectures that are being developed right now. So in my company, in Quantinuum, we have one of the leading ones, which is ion traps. And then there are architectures that are taking advantage of the properties of superconductors and superconducting junctions. There are others being developed that use neutral atoms, silicon defects, photonics, and I'm sure there are many other architectures that will emerge very soon.
So then I'm curious, what applications does quantum computing enable? I know, compared to traditional classic computing, what possibilities does this allow for?
That's really a very good question. I guess we can distinguish the possible application in two fields. One of them is solving, let's say, classical problems, problems that are in the everyday life, like, for example, solving partial differential equations or doing machine learning techniques, or solving optimization problems. For these kind of problems, there is some hints that a quantum computer is going to help, although this is still a topic of very active research because it's not totally clear where quantum computers will help. And then there is another area, which is the area of the simulation of molecules and materials. And in this case, the help from quantum computers is a much more clear topic, because basically what we are trying to do is to map a quantum system into another quantum system. And then it's much easier to see where are the advantages, although there are some caveats. But it's much easier to see where are the advantages of quantum computing in getting the dynamics of some material or some molecule, calculating different phases, etc.
So as you mentioned, Quantinuum focuses on the ion trap class of quantum computers. Could you further elaborate what an ion trap is and how that works and what the future of ion trap kind of promises for Quantinuum?
I can provide a very high-level view because I'm not a hardware guy. But yeah, basically, and this architecture of ion traps consists of a set of ions like ytterbium or other metal cations that are confined into some series of potentials. And they have two levels in their electronic structure that are well separated from the others. And with these two levels, you can define a qubit. And then you can manipulate information in this qubit by application of pulses. I think they use microwaves right now, although I will have to check. But basically, you have the qubits in the form of the two states of this cation, which is confined to this potential. And you have several of them. And then via these pulses, you change the occupations of these states, create superpositions of states, entangle them, all of these interesting quantum processes that we can exploit for information processing.
Can you explain exactly what qubits are? Maybe I missed this. Are they like building blocks in quantum computing? What exactly are they?
Yes, as you well said, they are the building blocks of quantum computing. The analogy is with a normal computer. In a normal computer, you have bits, which can be 0 or 1, and then you create these strings of bits, 0, 0, 0, 1, 0, 1, 1, 0, etc., which can represent numbers. A qubit is the quantum version of that, in the sense that this quantum bit can be 0 or 1, like in a classical bit, but at the same time, you can have a superposition of both states. It can be at the same time 0 and 1 with some coefficients. And that allows for basically considering strings of bits that are much larger than in a classical computer. You can compress lots of different configurations of these bits into small qubit register.
That was very helpful. And I think that now, this is a material science podcast, so we've kind of touched on the fundamentals a little bit. And so I want to bring in kind of how this might impact the material science industry and how material science is intertwined with quantum computing. And so I believe in a previous call, we discussed how quantum computing can be used to aid in the discovery of new materials, whereas traditional materials discovery and then the commercialization of those materials can be a very, very slow process that involves a lot of R&D, processing, and testing. So in your opinion, how can quantum computing play a role in making this roadmap more efficient?
I guess in order to answer this question, I would have to explain first what is the role of general computational material science and chemistry in this kind of material discovery process. Because this is a field that has been developing in the last 10, 20 years or something like that. Basically, the idea of using computers for materials research is, at least at the quantum level, at the electronic structure level, is basically twofold. On one hand, you can create large sets of candidate materials for some property that you're interested in. And with these computational tools, you can screen these materials, try to evaluate which of them are more promising for this property that you're interested in. And then once you have done this computational screening, you end up with a much smaller list of candidates that then you can check experimentally. And then you can continue working on them. So in this sense, you save a lot of money in terms of lab supplies and lab time, and basically the experimental framework. The second way in which computational methods help is in understanding. And I can give you the following example. Imagine you are doing some spectroscopy in some material, some interesting oxide or heterostructure. In your spectrum, you notice a signal which you don't understand why it's there. You have no idea. It shouldn't be there, but it's there. This means that something is inside this sample that is creating the signal. Well, if you have some ideas, some theories, some hypotheses, you can check them computationally. You can create, for example, you may imagine that this is created by some oxygen defect that has become injected into your sample. Then you create a model, you run your computational modeling there, you obtain your spectrum, and then you compare with the experimental one. And if the oxygen peak is there, then you say, aha, this is very likely that there's going to be some oxygen contamination in my sample or any other defect. This kind of stuff. And this is very common in general in computational materials and science. And in quantum computing, the way it can help is that for some subset of these materials, this kind of computational modeling is very expensive. And the materials in which this happens are usually materials in which the quantum effects are very strong. You have strong correlations between electrons, strong interactions. These are kind of systems in which classical machines struggle to perform these simulations. But for the quantum computing, for a quantum computer, in principle, this should be much easier. And in this sense, these kind of tasks that we do for simple materials in classical computers can be extended to much more complex and potentially more interesting materials with the help of quantum computing. And examples are, for example, oxide superconductors, metal insulator, exotic heterostructures, possibly topological insulators as well, many others.
So you mentioned that it would give us insight into more complex material systems, but you also mentioned how it could be used for more conventional material discovery as well. For that, how much more efficient is quantum computing, or is it really just that you're bringing a different approach to how you solve the problem, which allows for more understanding or a different analysis?
I think that both. So basically, quantum computers can, a bit related to what I said before, they can help in this material discovery process by being able to consider much more complicated candidates than with classical computers. And in the same way, if you want to understand phenomena happening in some material with this kind of very strongly correlated behavior, quantum computers are going to speed up your analysis and obtaining conclusions.
Another thing for current models is that for like machine learning models and other models, it's sometimes hard to explain the results of the models. For quantum computing, because now instead of just using a 0 and 1 as your inputs, is that going to change? Is it going to be harder to explain how the quantum model is actually characterizing the material system, or are there ways that we can make it explainable?
That's a good question. I have the impression that the only thing that quantum computer can do with this problem is that as you are considering more complex sets for your machine learning process, probably these criteria by which the machine learning method is obtaining your candidates, it might become a bit more obscure because of the increased amount of data you have to consider. Although I'm not sure. There might be the case that because of the quantum nature of the set that you are analyzing with ML, actually, interpretation, it becomes easier. It's an interesting idea. I don't know what to think. Worth considering.
Great. We'll look forward to it then. But I guess going back to more general questions for quantum computing is that what you said is it has a wide range of effects, but it can be used for drug discovery or predicting the weather, or creating a super clear pattern for applicable topics. What area do you think is going to be the most applicable and best use of quantum computing for the future?
Okay, I'm going to kind of lean towards my area of expertise, and I'm going to say that materials and chemistry are probably the most evident candidates for benefiting from quantum computers. There are plenty of problems out there that could benefit from having a good speed up thanks to this technology. There is one thing I would like to maybe mention, which is that there is this conception that quantum computers are going to replace classical computers in the future when they are totally developed. And that is not true. There are problems in which classical computers are perfectly fine and quantum computers don't offer any speed up. So in this sense, the quantum computer is going to be like when you use a GPU, that you use it for some particular sets of problems. So you can imagine that a computer system will have maybe a GPU, but it could have also a computer processing unit, a QPU, that you could use for this other subset of problems in which quantum computers are good.
I'm wondering from the material science student perspective or a young professional, is there a different skill set that you need to learn if you want to get involved in quantum computing, and in particular, this intersection between materials discovery, testing, et cetera, modeling, and quantum computing compared to the current computational material science classes and courses that we take right now?
I would say that what helps most is to have a solid understanding of quantum mechanics. Basically, learn your quantum mechanics at heart, because that is the basis for everything else. And then there are specializations. You can then specialize in the phenomena that happen in material science and in chemistry. It's also good to learn a bit about quantum information, what is a qubit and what is a quantum gate, all this sort of stuff, and how the information is processed, because that allows you to understand a little better the way these machines operate, and can help you, if you're an algorithms designer, that will help you a lot into designing algorithms for running on these machines for simulating materials. And if you are a user, you will be able to understand what are the strengths and what are the weaknesses of the algorithms you are using for running your simulations.
So from my understanding, quantum computers are much like more expensive, harder to upkeep. And so currently at school is like it's become very common to have like computer clusters to be able to do all this modeling. Do you think in the future we'll see something of the similar sort where like schools have quantum computers? Or I guess in the next 10 to 20 years, what degree of quantum computer utilization or industrialization do you expect to see?
Mm-hmm. Well, in the short to medium term, I guess, as these machines are quite complicated, I guess they'll have to be accessed via the cloud from some computing center sitting in some big research institution or some universities or some dedicated computing center. Farther away, it's possible that some kind of small size computers become more available for smaller institutions. But yeah, I would say that in the medium term, probably they will be sitting in large research centers or computing centers.
And then one thing that I also heard was that quantum computers, like you said, like travel and exchange information in qubits, but our computers exchange information in binary. And so there is a disconnect between the two systems. I guess I don't know how advanced it is. Is there still going to be a period where we're going to need more development in the communication between the two different systems for use in the cloud? Or has that been figured out to a point where now quantum computing needs to be more developed before being used more by the general public?
I think it still needs a bit of development. We are working, the community is working towards making it more accessible. For example, in my company, in Quantinuum, we have this package in Quantum for doing computational chemistry and materials on quantum computers, and that removes a lot of the complexity. But we're still not at the point of being able to say, just I give you this molecule, just run the simulation and give me all of the properties I want.
So something that I'm really interested in is that to hear more about where we were 10 years ago and where we are now for quantum computing with like simulating a molecule. How much development has been done in these last 10 years and how much development do you think will be done in the next 10 years?
Well, in the last 10 years, the developments have been really impressive. I remember when I joined that it was like a feat being able to emulate the hydrogen molecule. And now you can see regularly papers dealing with all sorts of molecules and materials, using many tricks. These calculations are still not qualitative in nature. They're not quantitative. But for example, I was attending a talk some time ago in which they were looking at, it was some oxide surface. And I thought, well, in 5 years, we are now able to do oxide surfaces with quantum computers. Although again, toy system, not very not quantitative at all. So that is the current state now. And in the following 10 years, what I expect is an interesting phenomenon, which is that I think the size of systems is going to become small again because of the following. The way quantum computers operate today is in a way in which there is a lot of noise injected into your results. Because qubits have short coherence times, they collapse into classical bits very quickly. They are very sensitive to external noise and perturbations. And the algorithms we have now are about trying to mitigate all of this noise. But when we have more qubits in the machines, we will be able to implement something called quantum error correction, which is basically encoding your physical qubits in such a way that they operate as a single logical qubit or virtual qubit, in the sense that if this set of qubits starts operating and one of the qubits has some error, the other qubits compensate this error. And so far, this approach hasn't been very successful because these error correction schemes require a very large number of qubits. But in the roadmaps of everybody involved in this field, it seems that the error correction will become available in some time in the future, in some years. And then in this case, you may end up seeing things like a computer with 1,000 physical qubits that become 2 logical qubits. And you're back to simulating the hydrogen molecule, but this time without any noise.
Yes.
And then from there, we'll start increasing again the size of the systems.
Cool. So yeah, maybe 2 follow-up questions. The first one is, so for these corrections of your qubit information loss, is that a mechanical, like a solution where you can create better mechanisms to have more precise like measurements of your qubits? Or is it like a software, like how you like understand what the value you're getting from it is?
It's both of them. On one hand, you need to make sure that your qubits have an error rate that is below some threshold. So that's an engineering problem. And then on the other side, you need software to encode, to make these encodings of these big logical qubits in the most efficient manner. So both of them are being investigated in this sense.
Got it. And then my second question is, when we talked in the very beginning, you talked about ion trap as a mechanism for you to be able to use qubits to do this work, but you mentioned a few other systems. Do they have different error rates, or what's the main difference between those systems and like the accuracy and like what they look in 10 years, or will they all get to the same point, do you think?
Probably there will be some differences. We are already seeing differences right now in different architectures. For example, I can provide a quick comparison between the two most popular architectures, which are superconducting junctions and ion traps. The difference between them is the following. In general, superconducting architectures are noisier, but they are quicker to operate, while ion traps are the opposite. They have much less noise, but getting the results is a slower process. So one has to leverage these strengths and weaknesses of each architecture in order to make the computer work.
Interesting. So back to kind of the noise sensitivity and the potential error rates, which seems like one of the current drawbacks of quantum computing. You talked about how engineering will play a role in overcoming this obstacle. What does that look like? What type of engineering innovations do you think are needed to address this challenge and any potential other shortcomings of quantum computing?
There are many things. For the current architecture, for example, you have to better lasers, better refrigeration, better control of all the fields that keep the ions in place, for example, in the Quantinuum architecture. Then there is also a lot of research into alternative qubits. Like, for example, Microsoft is investigating topological qubits, which are supposed to be much more resilient to noise. There is also all of this research into silicon qubits, in which you exploit the levels of silicon surface defects, and that has its own advantages and disadvantages. So I would say improvements are needed in the full stack of the machine.
Just tying that back to materials engineering, I know you mentioned kind of getting involved in quantum mechanics or, taking a quantum mechanics course, learning about quantum information. Is there anything else that you think material science and engineering students and young professionals who may be interested in quantum computing or getting into this industry, should they look at any resources or should they take any other courses, get involved in any other experiences to best set themselves up for making an impact in this industry?
So university courses are in general quite good. You can also check this resource provided by IBM, which is the Qiskit textbook, which provides a perspective on quantum computing from user experience. Also, as a kind of a general rule of thumb, I would say try to get also a bit of understanding of the different kinds of materials that are out there and the difference between, for example, focusing especially in strongly correlated materials, because those are the ones that are the most difficult to address, and these are the ones that should be addressable with quantum computing.
And yeah, so I think that as the new generation got more access to computers, they were able to play around with like coding and be able to implement their own things and create these new applications. I guess, do you ever see a time where someone could do this similar thing with quantum? And then how much time do you think quantum needs to mature into that ecosystem to allow the hands-on application when we're much younger in like high school going into college?
I think we need a bit more of development on the software side to make things a bit easier, but I don't think we are very far from there. Right now, the community does the developments using the Python language, using Python scripts and modules, which is in itself a language which is easy to learn. I just think we need one extra layer of simplicity to make this amenable to high school teaching.
That'll be super exciting. And so then I was wondering, do you think that quantum computing will like exactly mirror the adoption curve of classic computers? I know you mentioned that it doesn't need to replace classic computers, but I was just wondering down the line at some point, if costs come down, then and it's more efficient, faster, do you see quantum computers, I guess, ever being just like general use and anybody can get one, or do you think it'll kind of stay at a certain level above that?
I have the impression that this technology is going to be a bit like HPC, that is not something that you'll be able to install in your desktop machine, something like that. But I might be wrong, and that would be quite pleasant.
Well, if there's nothing else, then thank you so much, David, for joining us today. This was really fascinating conversation, and I'm excited to see Quantinuum continuing to make an impact in this space and innovating rapidly.
Well, thanks a lot. It was a pleasure.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.